I was gonna do something today, but maybe we should do something else.
It's like a lot of people may have already left for break.
It feels that way. Think about what to do here. Okay.
Some company.
I was going to give some homework hints today. Maybe I'll focus on that instead of doing what I was going to do. Anyway, that section, was it 5.4, called The Mathematical Theory of Power Series? Probably.
Sounds plausible.
Yeah.
Sounds plausible.
So that has some fairly interesting exercises to challenge your understanding of radius to convergence. So the Hadamard's formula, I was going to prove it today, but you want to see that? It's kind of fun. Maybe I'll post a different lecture than I actually give for the rest of the class, because I've definitely got recordings of me proving this elsewhere. Yeah, this is a fun thing, and it's remarkable that Hadamard figured it out, because you have to be kind of clever to see it. But once you see it, it's not terribly hard to demonstrate. So the famous formula is that the radius of convergence exists and equals r, where it satisfies this identity. 1 over r is the lim sup of the nth root of the modulus of an, coefficient an. Kind of hard to believe. And it's r equals 0 and r equal infinity are allowed in this formula. When r is 0, of course, that means that lim sup is infinite. That lim sup is always greater than or equal to 0. If that goes off to infinity, then it's the r equals 0 case. And if r is equal to radius of convergence is infinite, that means it converges for all complex numbers z. And that stands for r equals 0 is the lim sup is plus infinity. And r equal infinity is the case lim sup equals 0. So those cases are allowed. And notice, so there's the definition of what the lim sup is. It's the limit of the sup of those things over the sup over the sets where we toss out the ANs one by one. So n greater than or equal to capital N. Okay, that means we toss out the first few terms until we get to capital N. And that means that those numbers can only get smaller, because, of course, these numbers here are greater or equal to 0. And so that sup, whatever it is greater or equal to 0. And as I toss out more and more terms, the sup can only go down. So this sequence can only go down. Can only decrease or stay the same. So it can only decrease or stay the same as we toss out early elements. Toss away the ANs. But that's what some books would call that a decreasing sequence. But more accurate term is a non-increasing sequence. Non-increasing. Can never increase. So remember that famous theorem you learned in Math 341 of a non-increasing sequence that's bounded above has a limit. So that limit is guaranteed to exist. So a big fact from Math 341. A non-increasing sequence. I'm sorry, what is it? It's bounded below. So these things are all greater than or equal to 0. A non-increasing sequence bounded below has a limit. So the big word is has. It exists. The case where that thing would be infinite would be those soups would always be infinite. So that would be that sequence would be infinity, 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 and so of course that's not that limit wouldn't be zero, a finite number. It's infinity. So that's a special case of it. So the special case the lim sup is infinity, then that sequence is infinity, 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 etc. Okay, so those are sort of easy facts. That means that lim sup exists no matter what. Okay, so the way to think here. So we're going to think those soups supremum, also known as the least upper bound. Did I mention that? Yeah, the sup is equal to the least upper bound. Okay, so those soups are sliding. Think of them as sliding down to 1 over r. It can only get smaller. Okay, so a typical picture when you're going to mess around with power series is we start out with a big circle of radius. Let's see, this is going to be the radius of convergence, capital R. So here's Z naught. I'm going to take the radius to be capital R. And then I'm going to take a slightly smaller circle. This is kind of if I was going to do the Cauchy integral formula. I would do it on a smaller circle. I'll let that be radius little r. And then I'm going to take an even smaller circle, just in case. So there's r. And then I'll take a smaller one, radius rho. And those z's I'm going to take are going to be inside this smaller circle when I start thinking about convergence. Okay, so let's see. We're going to have 0 less than rho, less than little r, less than the capital R in the Hadamard's formula. Okay, that means 1 over r is less than 1 over little r And that's less than 1 over rho. Okay, and we're thinking about the soup sliding down. So they're sliding down to 1 over r. Soup of the nth root of an modulus, as n is bigger than or equal to n, is sliding down to 1 over r. So eventually it's less than 1 over little r. So there exists an n, natural number, such that the soup of the nth root of mod an, such that n is bigger or equal to capital N, is less than 1 over r. Maybe I should call that n naught. Since they only get smaller, that would be true for all the n after n naught too. I don't think I care about that at this moment. Okay, so this shows us that 1 over r is an upper bound. And that soup is the least upper bound. So what does that? That means that the nth root of mod an is less than 1 over r for n bigger than or equal to that n naught. Okay, let's think about what that means. Let me take powers here. Take the nth power. That would tell me that an, when I take the nth power, is less than 1 over r to the n. For n greater or equal to n naught. And now we get something interesting. Now we have, let's multiply by z to the n. Modulus of z to the n. Then I would get a n z n modulus is less than the modulus of z to the n over r to the n. And of course, if z is inside that circle, that's going to be, if z is in the picture there, remember z was in an even smaller circle, that's going to be less than rho over r to the n. And so the aha here is, sure enough, that shows the power series converges. By the way, I should have taken, I'm taking z naught to be 0 here. Otherwise, I'd be writing z minus z naught. And so the power series converges by comparison with the geometric series. That's our big tool. Of course, it's important that rho over r be less than 1. Strictly less. Okay, it's important that be less than 1. Check. And I could also deduce by this estimate that the series converges uniformly. So on the smaller disk, on the disk of radius rho about z naught, which I took to be 0. I've done that before, so I won't do that again. And now the last step in the argument is to see that the series diverges outside that radius. And that turns out to be a snap. Last step, show that the summation an z to the n diverges when mod z is bigger than r. Okay, so now let's see. If mod z is bigger than r, that means that 1 over r, what does it mean? It means that 1 over mod z is less than 1 over r. Okay, so we have 1 over mod z is less than 1 over r. And remember, those soups are sliding down to 1 over r. So 1 over r is less than or equal to that soup of the nth root of an, such that n is bigger than or equal to capital N. Well, that means there's got to be something kind of big in that list of things. That means for each n. So, for each n, because of that inequality, there's got to be something in that set that's bigger than 1 over r, or at least bigger than or equal to. There exists an n, such that the square root of the nth root of the square root of whatever, you know what I mean, the nth root of modulus an is greater than or equal to 1 over r. Otherwise, that soup couldn't possibly be greater than or equal to. Let's see. Oops, let's see, I got to, did I say less than 1 over? It's less than, oops, I messed up here. That's not strictly true. That could, all of those things could be, yeah, let me think about this. It was important that I have a strict inequality here, because what I just said here isn't 100% right. Since 1 over mod z is strictly less than that soup, then there's got to be something that in there that's strictly bigger than 1 over mod z. Okay, since 1 over mod z is strictly less than that soup, there's got to be something in that list that's definitely bigger than 1 over mod z, since it's the least upper bound. Because if that would mean that 1 over mod z is even less than the least upper bound. Okay, this is where it gets, where you have to think about the meaning of the words and the symbols. Okay. So I should say here, otherwise, 1 over mod z is less than the least upper bound. Is an upper bound. That is less than the least upper bound. And if you think about what that means, now if I multiply, let's see, if I take the nth power, I would get 1 over mod z to the n is less than an. And then the aha moment is I found an an such that 1 is less than an z to the n. For that n, which was bigger than my capital N. So for every capital N, I can find you a little an that does that. That means they're not bounded. I mean, that means the terms can't possibly go to 0. The terms of the sum an z to the n don't go to 0. So that means the series diverges. And that's what we wanted to see. Check. Questions about that? Okay, now I want to start using it for something. So it's kind of a rule of thumb. If you're going to check about power series convergence, check ratio test first, maybe. Root test second. And then Hadamard. Because Hadamard isn't exactly a formula that you can compute with, whereas the other ones are. In that order. And then after that, you can get desperate. Like that Fibonacci thing. It's kind of a last resort thing to do. Let me show you an example that I like. Very often when you use power series to solve differential equations, you would get a recursion formula. Let's take the summation as n goes from 0 to infinity of an z to the n, where a naught, let's see. I want to do this. Let's take a naught plus a3z cubed plus a6z to the 6th plus etc., where a naught's equal to, say, 1, or pick any number you want, and then we recursively define coefficients as a n plus 3 is equal to something screwy, like, how about n plus 1 times n over n times n plus 3 times n plus 7, something ugly and weird, times the previous n. So I build up a series for n equals 3, 6, 9, etc. So finding the coefficients would be a bear. And Hadamard's formula would be tricky. But the ratio test, here's how I like to think about the ratio test. I take the limit of a u that's way out there. and I divide by the u that's right before. And I take the limit as the way out there goes out there. So that's kind of a dopey thing to write. But that's exactly what the ratio test is. You take a term that's far out in the series and divide by the one that's right before it. Okay? And so in this case, that's going to be equal to the limit as the n goes to infinity and those an's. Let's see, I'll pick one that's way out there. How about a n plus 3 times z to the n plus 3? And n is big. Well, the one before it would be given by an z to the n. And notice if I was trying to use the ratio test for the series without doing this, I'd be dividing by zeros. The one before the an plus 3 one is 0. So the formula wouldn't make sense from the point of view of the ratio test if I did it the term that had 1 degree less. Okay, so that limit is going to be easy to calculate because, let's see, that's equal to the limit as n goes to infinity. The an plus 3, I forget my recursion formula. It's n times, there it is. Let me copy this. That's the ratio of an plus 3 over an. Oops. Okay. So that's an plus 3 over an. And now let's see, z to the n plus 3 over z to the n in modulus is z cubed. I don't like my recursion formula anymore. I'm going to change it. I'll make this, how about n plus 13? How about 2n plus 13? Why not? Then you know how to compute that limit above there. Let's see, n over n, of course, it goes to 1, and n plus 1 over n plus 3 goes to 1. And 2n over plus 13 over n plus 7 goes to 2. So this limit is equal to 1 times 2 times z cubed. Okay, so that limit is modulus of z cubed, and the ratio test tells me if, 2 times z cubed. And the ratio test tells me if that's less than 1, we get convergence, and if it's greater than 1, we get divergence. And so if I put the 2 on the other side and then take the cube root, I would get mod z less than 1/2 to the 1/3. 1 over 2 to the 1/3. I get convergence. And if mod z is greater than that, I get divergence. And that exactly means that the radius of convergence is 1 over 2 to the cube root. Okay, so the ratio test there is a very straightforward thing to do. Another example, now that I've done Hadamard's formula, I'm not afraid to use it, but it's Hadamard's formula. I studied this by other means earlier, by comparison with geometric series and things like that. But this was a famous power series because it has a lot of holes in the sum. A lot of the coefficients an are 0 because n factorials start spreading out like crazy. And so we see here that an is equal to either 1 or 0. It's equal to 1 when n is equal to an n factorial, some factorial, and otherwise it's equal to 0. Well, so those soups, if I look at those sets, the soup of the nth root of an, mod an, there's certainly a big thing out there that's bigger than n, that's a factorial. And so at least one of those things is 1. So that's either zeros or ones, and there's at least one out there. The soup of such a set is equal to 1. And of course, that's 1, 1, 1, 1, 1 for all n. And so that thing has a limit. One over r is the limit of those ones. So r is equal to 1. I deduced that by other means, sort of using more theory of power series the first time I did it. Oh, let's see. I've got some other. Oh. Let me see if I can find some better examples that are kind of like the homework. Oops. Oh, darn. For crying out loud, I can't find it. Let's see. More about. I think this might be related to one of the homework problems. Let's look at summation n equals 0 to infinity. 2 to the n, z to the n squared. So the book, I hate this formula that's in the book. I hate the formula. What is the formula? If the limit as n goes to infinity of an, this is the upside down of the ratio test. If that limit exists, then it's equal to the radius of convergence. This is true, but if there's lots of gaps in the series like there is in this case, too, there's a lot of those an's are 0 if it's z to the n squared. And so that formula would be useless there. True, but often some of the coefficients are 0 and you can't divide by 0 in that formula. And very often that limit doesn't exist. So, but series with lots of zero terms ruin the formula. And this limit doesn't have to exist. It exactly exists when you can use the ratio test somehow. And you might have, but you cannot, yeah, often does not exist. So that's why I hate that formula and don't. You had to prove it as one of the homework problems, and it's a rather straightforward application of the ratio test. And so I rather use the ratio test every time than memorize this formula. But it's a true formula. But let's go back to this one I have here, the summation of 2 to the n times z to the n squared. If I use the ratio test directly, let's see what happens. Let's try the ratio test. Okay, I would have the ratio. Let's say I'll take a term way out there. A term way out there and the term right before. U sub out there divided by U before. Let's see, the one that's way out there, why don't I take that to be 2 to the n plus 1 z to the n plus 1 squared. Okay, that's a term that's out there, if n is big. And the term right before it would be 2 to the n, z to the n squared. Okay, so that is 2 times the modulus of z to the n plus 1 squared minus n squared. That equals 2 to the modulus of z. That would be 2n plus 1 when I do the algebra of that power. And I'm dying to use the ratio test. And you look at that and ask yourself, when the heck is that going to be a bounded thing? If the modulus of z was bigger than 1, that would just get bigger and bigger and go off to infinity. So it certainly wouldn't be bounded by 1. And good news, when mod z is less than 1, then it goes to 0. So the aha is, when mod z is bigger than 1, the limit of those terms, let's call it the limit of those things, would go off to infinity. And that means you get divergence. And when modulus of z is less than 1, then that limit goes to 0, which is strictly less than 1. And so the ratio test would tell me that that series converges. And so we conclude that the radius of convergence is equal to 1. Okay. see, could you use the Hadamard? Let's think about it. I don't want to think about it. Oh, let's see. Another example from homework like. Let's think about sum n goes to infinity 2 plus minus 1 to the n. To the n. Times z to the n. That's kind of two series in disguise. That coefficient in there is either, let's see, what is it? It's either going to be 1 or 3, right? This equals 1 or 3. And so let's see, it's equal to 1 if n is odd. So that would be, this when it's 0 would be 3. 3 plus z plus 3 squared z squared plus z cubed plus etc. 3 to the 4th z to the 4th plus z to the 5th plus dot dot dot. So you can pull them apart actually. And you would get 3 times sum of, what? No. You get the sum of 3 to the n, z to the n, when n is even, plus the sum of z to the n when over n odd. And those have two different radii of convergence. And so you, when you add two things, the radius of convergence is a sum equal the minimum of the two radii. And let's see, what's the minimum? Well, the other one, the second one, clearly has radius of convergence 1. And that, if I did the ratio test on the first one, I bet I would get radius of convergence 1/3. So the minimum is going to be 1/3. So sometimes you can get sneaky like that and avoid. If I stuck that mess into Hadamard's formula, I'd have to think about it. It would work, but I have to think harder. Oh, let's see. Let's see. You guys have any questions about anything? Well, thanks for coming today. I assume you got your papers back, right? Yeah. Any questions about anything?
I think for question 5 in section 5.2, I guess it gave some.
What was that series?
I think it's about Taylor series.
Okay.
But like the point is, it said something about state the Taylor series and the radians of convergence, and then, I saw earlier in the textbook, like if the series is entire in the whole plane, then it has to be that the radius of convergence has to be infinite.
Right, because we had this fact. Yeah, so let's see.
So like, do we
R equal infinity means that the f of z that you get, which is the sum of the power series, is entire. That's the case R equal infinity it means that lim sup would be 0. So what was the...
As in, I'm wondering, in that case, do I need to like derive the Taylor series for those expressions, or?
Oh, I wish I knew what the question was. The number. You don't have the book, do you?
I have it on my computer, but.
If you can give me a. So the Taylor's formula.
Well, section 5.2 is about the Taylor series.
Yeah.
In the meantime, super quick question.
Uh-huh.
When we went over Hadamard's formula, and we were saying that the suits were sliding down, is that as we're increasing capital N?
Right.
Okay.
It's as capital N gets bigger, those things can only get smaller.
Okay.
And so think of them as sliding down.
So
Number
this question.
5. Which one?
So like in general, because it says find and state the
Oh,
convergence
okay.
properties. So do I need to derive the Taylor series if I know it's entire anyways, or?
State the conversion for the following. Okay, so that's the question. Here's the fact that question is. So what problem was that? Number 5 in section what?
5.2.
5.2, problem 5.
Yeah.
So the thing we knew is that if a function is analytic, f analytic on this region here, then if we're trying to find a power series, I use the Cauchy integral formula to do this. I can find told me I could find a power series that would converge on that set. So the radius of convergence of the series for that little f at z0, and here's the important thing, it's greater than or equal to the radius of this circle, the biggest circle I can stick in there. Okay. Well, if that function has a pole someplace, so I saw one of your examples was 1 over 1 plus z. And where's the center for that one?
0.
1 plus z. Okay, so that has a nasty, no, oh, it's 0. Okay. So on the complex plane, this has a nasty spot at -1, a pole there. And you were trying to get the radius of convergence about 0. And so this fact about power series, that if it was analytic on a set, the radius of convergence has to be bigger than or equal to the radius of that biggest circle you can stick. So we see that the radius of convergence is bigger than or equal to 1. But that pole means it has to be less than 1 too. Because if the radius of convergence was bigger, then that function would converge to something that doesn't blow up there. And so the pole means that r is less than or equal to 1 too. So r equals 1. I believe that's what they want you to do there. You don't have to calculate anything. That's the thing. I mean, right, it's not calculating. It's using this fact.
I see. So in general, for all poles, is it true that the radius of convergence is the distance to that from the point to the pole?
If it's a rational function, that's true for all rational functions, yeah. And if the function was something else, like if I put an e to the z on top of that, yeah, the pole would be what kills it there. That would be analytic on that same picture, and it would blow up at the -1. If the thing on top had a 0 at -1, then I'd have to think about it, because then there would be some cancellation happening.
Okay.
Okay, well, I'm glad.